In this video, we're going to begin looking at the chemistry of organometallic compounds. And what you'll find here is that this material is essential material for future chapters, for 15, for 17, 18, 19, 20. Okay? So there's going to be some reiteration of the topics that we talk about in this chapter. So this is just kind of a foundation chapter for the next few chapters is the way to regard this. Okay? All right. So what do we mean when we say an organometallic compound? An organometallic compound has a bond between a carbon and a metal. All right? So, and this is the most common type of organometallic compound that we're going to cover in this chapter. This is where the metal and the carbon make a sigma bond. Okay? All right, notice how almost all of the elements that we refer to as metals are less electronegative than carbon. So if you look at the dipole, it goes that way. So there's negative charge building up at carbon. And the less electronegative the metal, or the more electropositive the metal, the more negative charge character there is at carbon. Okay, so when we look at metals that are on the far left side of the periodic table, we can make kind of the loose connection that the reactions that they do are kind of resemble what the free carbanion would do. Okay? Most of the reactions that we're going to talk about involve these two types of organometallics shown at the bottom here. An organolithium compound, exemplified here by methyl lithium, okay, and an organomagnesium compound here. Recognize that magnesium's in the second column of the periodic table, so we have to have this bromine here to fill the coordination sphere. Okay, so the organometallic or the organomagnesium compound is named after its discoverer, Victor Grignard, one of the earliest winners of the Nobel Prize in Organic Chemistry. Okay, so this is just going to be referred to as the Grignard reagent. Okay, we can always tell people that don't come to class. They call it the Grignard. Okay. All right, if we look in the periodic table, what you find is that lithium is less electronegative than magnesium. Therefore, the organolithium reagents are going to be more reactive than Grignard reagents in most of the reactions where we use them. However, I think for most of the reactions that we actually discussed, these two are pretty much interchangeable. Okay, so let's look at how we form organolithiums. Organolithiums are formed by the reaction of an alkyl halide. Important here that it has to be a halide. This is one of the reactions where we just can't substitute a tosylate for a halide. Okay? And this reaction in the balanced equation will produce the organolithium reagent and 1 mole of the lithium halide as a byproduct. All right, so all types of R groups here pretty much work. R can be sp3, sp2, or sp carbon. The only structural limit on this R group is that it just can't contain another group in it that's reactive to an organolithium reagent. You'll appreciate that in a couple of slides when we look at some of the reactions that organolithium reagents actually do. All right, so chlorobenzene would react with lithium to make phenolithium. This alkyl iodide here would react with lithium to make the compound where iodine is replaced by lithium. Okay, iodine gets replaced by the carbon-lithium bond. All right, here's the mechanism. I don't think I would ever ask this mechanism on an exam, but this is basically what is occurring. We're transferring the electron to one of the empty d orbitals that bromine would have available to it. Okay, or in some cases there's a sigma antibonding orbital available too. This will make the radical anion shown here. The radical anion can now lose bromine, and this is going to generate now the free radical, and this is going to react with our other mole of lithium. Notice that we need 2 of them to make the organolithium reagent. Okay. All right. What about the Grignard reaction? Okay, the Grignard reaction is almost always done in ether, and our limitation here is pretty much the same as it is with organolithiums. The X has to be chlorine, bromine, or iodine. Tosylate is not an optional substitute for a halogen in this reaction. And the R group cannot be anything that's reactive to a Grignard reagent. It's almost always done in ether. This is because this makes the magnesium complexes to the oxygen lone pairs in ether groups, and that tends to stabilize the Grignard reagent a little bit. Okay, R just can't be anything reactive to a Grignard reagent, so here's a few examples. This allyl chloride makes the allyl Grignard. This bromine here, where the bromine is actually attached to sp2 carbon, makes the Grignard reagent, no problem. You can make a Grignard reagent in the presence of an ether. That's one of the functional groups that's okay. Obviously, alkenes are okay, as you can see by these examples too. And this will turn the iodide into the corresponding Grignard reagent. It really makes no difference what the halogen here is. They're all pretty much of very similar reactivity. It might make a difference in the yield or something, but on exam papers you can have any halogen you want here pretty much, except fluorine. Okay, right. Let's look at the reactions of organolithiums and Grignard reagents. And reaction number 1, we'll say, is protonation. Okay, so CH3Li is sort of like CH3 minus. CH3 minus, it's the conjugate acid of methane, which has a pKa of about 60. This is a very high number when you think about what pKa means. It's a logarithmic scale. This is 10 to the minus 60 moles. This means on planet Earth, all the methane molecules on planet Earth, it's likely that not even one of them is deprotonated, okay, at equilibrium. All right, anything with a pKa of less than 35 or so readily protonates an organolithium or a Grignard reagent, okay? So if we were to take the Grignard reagent shown here on the left and treat it with an alcohol, cyclopentanol shown here, we would turn the carbon magnesium bond into the carbon hydrogen bond. Okay, let's just change the structure of that. Okay, all right, so hydrogen replaces the metal, and what happens here is that the alcohol turns into the magnesium alkoxide. All right. Let's imagine that I'm going to treat this molecule with a different compound, deuterium oxide, instead of hydrogen, instead of water with hydrogen in it. Okay, what you'll find here is that you actually add a deuterium. Okay, so this is one of the most common reactions used for labeling a compound. We've seen deuterium labeling in the past. This is how, or this is one of the main reactions that introduces that deuterium label. All right, what about this Grignard reagent here? Could it exist? Well, it can't, because it would have absolutely no lifetime. The very instant it's formed, within a millisecond or a nanosecond or whatever, we would find that this acidic hydrogen basically transfers itself over to here, and we would end up with this compound that doesn't have any sort of carbanion character at all. Okay, we would just end up with a magnesium alkoxide of 1,2 of N-butyl alcohol. Okay, and we would not get any of the Grignard type reactions occurring with that compound. Okay, so we would not want to make a Grignard reagent that has an alcohol functional group in it. Okay, why is it that we have this limitation 35 or so? Why don't we just say 59? Well, this is because the organolithium bond is mostly covalent, okay? It's not truly an ionic bond, okay? So it has to, because it's not truly a free anion, it just doesn't just randomly exchange protons with everything. It has to be, the proton has to have some level of acidity before it can be removed with the Grignard reagent. Okay? All right, let's just review carbanion stability, or pKa's, from the past. This is, I call this table hydrocarbon acidity, but you can see in this table that not all of these things are actually hydrocarbons. Okay? All right, so hydrogen at sp carbon is more acidic than hydrogen at sp2 carbon. Okay, the pKa of a terminal alkyne is about 25. The pKa of alkene hydrogen is about 40. Okay, this is a lot more acidic than the hydrogen on methane, which is about 60. Water, remember I told you in the previous half of the class that you always have to remember that water has a pK of around 16, and ammonia has a pKa of around 33. All right, here's our conjugate bases: the acetylide, the vinylide, methyl anion hydroxide, and amide anion. Okay, the enhanced acidity of the alkyne, remember, is due to the percent S character. The S orbitals get closer to the positively charged nucleus, and having excess electron density in an S orbital is a little bit of a stabilizing influence. So the carbanion orbital here, and we're assuming the carbanion orbital corresponds to the orbital that the hydrogen was attached to in the species in the far left, is a 50% S sp, 33% S in sp2, and 25% S in sp3. All right. This is the number one reaction, and this reaction is going to be an essential part of future chapters. Okay, and this is the carbonyl group addition reaction. Because there's a partial positive charge here, we can add a nucleophile to this center and make an alkoxide. All right, so here's the arrows. Get used to seeing these arrows. You're going to see them a lot. Let's just draw the lone pairs there to so you can sort of see what is going on there. All right, so the nucleophiles will add to carbonyl carbons to turn the sp2 carbon into an sp3 carbon. And after protonation of this alkoxide, you'll get an alcohol. All right, just since we haven't had ketones and aldehydes yet, let's just review a nomenclature issue. We call it an aldehyde if one of these R groups is a hydrogen. We call it a ketone if neither of these R groups are hydrogens, if both of the R groups are actually carbon groups. And we call it formaldehyde if both of the R groups are hydrogen. And formaldehyde is not a class of compounds. There's only one. It's a unique compound. All right. right, so we're going to treat a ketone or aldehyde with a Grignard reagent. We're going to make the alkoxide, and we're going to treat it with mild H3O+. I always say H3O+, but it really doesn't have to be very acidic water. In fact, water itself in large excess will actually do this quench just fine. Okay. An organolithium reagent does exactly the same thing. Okay, we make a lithium alkoxide, and mild acid again gives us the alcohol. When we have an aldehyde doing this reaction will make a secondary alcohol. A ketone doing this reaction makes a tertiary alcohol. Formaldehyde doing this reaction makes a primary alcohol. Okay. All right, let's just look at the mechanism. I'm going to take a little bit of creative license here and say that the Grignard is a carbanion, but we can think of it as doing a nucleophilic addition like that. We're going to find later on there's a couple of cases where this carbanion analogy doesn't work, but for the most part it works nicely. All right, so let's do a little question here. Which of these compounds could form a stable Grignard reagent upon reaction with magnesium and ether? All right, so first one has an extra halogen in it, but this halogen but fluorine doesn't really react with magnesium. It doesn't really react with nucleophiles either. So this one would be no problem. That would be a perfectly stable Grignard reagent. All right, this next one has an active OH group. We cannot make a Grignard reagent here. This is because of the presence of this acidic proton. We'd see that our Grignard reagent would spontaneously react with the hydrogen that's in the molecule. It doesn't necessarily have to react intramolecular. It can react with another molecule of itself, and eventually you're just going to make the compound that's an alkoxide. All right, this one is fine. Ethers can make Grignard reagents without any problem. Okay. In fact, remember that ether is the preferred solvent for making a Grignard reagent. Next one, we cannot make a Grignard reagent from this. This is because we have a group, an aldehyde group here that's reactive to Grignard reagents. So the minute you make that Grignard reagent, it'll spontaneously add to the carbonyl group. This one, it can't do an intramolecular reaction because there'd be a lot of angle strain, but it can react with a different molecule of itself. And if that happened, you would make this, and then it would find another molecule of itself, and you'd probably make a compound that has a very high molecular weight, a polymer. Okay, and this last one, we're doing something we commonly did in the first half of the course, substitute a tosylate for a halide, but this is the one reaction where you cannot do that. So this last one would fail. This is because tosylates are not interchangeable with halides in the Grignard reaction. All right, let's look at some examples. Try to predict the products here. All right, so the first one, we have a ketone, and it's reacting with a vinylic Grignard. A ketone is going to make a tertiary alcohol, and that's our product. And by the way, this H3O plus here, just want to reiterate, it's very mild. It really isn't capable of doing anything except just quenching the reaction. All right, and this third one, we're adding the Grignard reagent to an aldehyde. The aldehyde has an alkene in it, but the reaction still occurs at the carbonyl group, and this is the one that we'll make. Recognize that we do have two chiral centers here, so if you did this reaction, it would be a mixture of diastereomers, but the way I've drawn it so it implies that we don't care about stereochemistry in this problem. All right, this is not a Grignard reaction. This third one, it's the making an anion. Okay, so in the first one, we make the carbanion, but remember a carbanion is like a Grignard reagent, so it will react in the same way. Formaldehyde is our carbonyl compound, so when we add it, we're going to get a primary alcohol, and there is our product right there. Okay. And in the last one, we have a organolithium reagent that has an ether group in it. And everything that's to the left of lithium is going to end up in our product, and we're going to get that tertiary alcohol that you see right there. Recognize that if you look at the tertiary alcohol that you formed, in each case, the bond that you made is a bond to the alcohol carbon, and that's an important point for the next problem where we're actually going to look at things in a retrosynthetic way. Okay, so this is the retrosynthetic arrow here. Okay, this means what did we need to actually make that compound? And recognize that when you have a tertiary alcohol, you actually have three different combinations of Grignard reagent and ketone that can give rise to that alcohol. Okay, and I'll say when we look at making bond A, that means R1 has to be the Grignard reagent and the other R groups are in the ketone. When we make bond B, R2 is in the Grignard reagent, the other R groups are in the ketone. And when we have R3, when we make bond C, that means R3 is in the Grignard reagent and the other R groups are in the carbonyl compound. Okay, this is if you have a tertiary alcohol. If you have a secondary alcohol or a primary alcohol, you have fewer options. Okay, since one of those R groups will be a hydrogen. Okay, we're going to see later that we can add the hydrogen as a nucleophile as well, but not as a Grignard reagent, or not as HMGBr. All right, so how do we make this compound here using the Grignard reagent? All right, so what are our bonds? These are the bonds that we would make. We would make the carbon-carbon bonds going to the sp3 alcohol carbon. Okay? So the carbon, this carbon here will be part of the C double bond O group. All right? And all of our choices. That's an important point to remember. Okay, and we're bringing in the whatever's on the other side of these slash marks through the Grignard reagent. All right, so we have two possible ways to make this aldehyde, just one. Okay, in the bond line diagram, of course, there's another hydrogen here that we're missing. Okay, so let's just remember that hydrogen is there. All right, so there are two possible combinations. We could take parachlorobenzaldehyde and this butynyl Grignard reagent, or we could take the Grignard reagent that's derived from, that has a parachlorophenyl group, and treat it with the aldehyde shown here. Okay, since it's a secondary alcohol, this means that our precursor carbonyl compounds are aldehydes. Okay, now, which of these would you use? Well, what you do is you get yourself a chemical catalog, price these things, see which one is cheaper, and that would be the route that you would use to make the compound. That would become the preferred route. Okay, the cheapskate idea is how you. It's kind of underappreciated, but if you actually do organic chemistry, it's something that you have to worry about quite a bit. Okay, and I think that the top route is going to be cheaper to do. All right. Okay, this last problem here is just a classic type of problem that you encounter in the Grignard/organometallic chapter, where we're going to take a tertiary alcohol like this one. It's unsymmetrical. It means that if you look at the groups attached to the alcohol-bearing carbon, there's 3 different groups there. And we're going to design 3 different combinations of Grignard reagent and ketone that will give rise to this compound. As before, pause the video, do it yourself, and then restart it when the answers appear. All right, so how do we approach a problem like this? One thing you would want to do is just imagine looking at each of the CC bonds that connect to this carbon right here. That's the carbon that's attached to the alcohol. All right, so let's just imagine this one right here. All right, everything on one side of that slash will come from the Grignard reagent, okay? Everything on the left side of that will come from the Grignard reagent. Everything on the right side, that is the side that includes the alcohol-bearing carbon, will come from the ketone. All right, so here we actually have 3 different CC bonds exactly like that one, okay? I've just labeled them A, B, and C. All right, so what do we do here? Well, we're just going to imagine A comes from a phenyl Grignard. B comes from what I'll just call this whole group here isopentyl. So that'll come from an isopentyl Grignard, and C will come from an allyl Grignard. All right, so here are the combinations. Combination A, which we discussed before, the aryl or aromatic Grignard plus the ketone that has all the other things in it. Okay. Again, this one is done by my slash mark there. Okay, in the original problem, and B and C give us these 2 other examples right here. All right, and that's where this video ends. Next one will feature some other types of organometallics beyond magnesium and lithium.